Question 4. A compound C10H12O2 whose spectrum is shown here was isolated from a reaction mixture containing 2-phenylethanol and acetic acid. Propose a structure for this compound. Assign peaks to show which protons give rise to which signals in the spectrum. Well, I would start by looking at the molecular formula, and immediately you can see that HDI is 5. Okay, so the HDI is 5. There's 12 protons in the compound. You can see here, if you can't read it, it's a 3 here, a 2 here, a 2 here, and 5 here. So 5 plus 2 plus 2 plus 3 gives you 12. So that tells you that this first, or the most deshielded protons here, represents 5 protons. This here is 2 protons. Over here we have 2 protons. And then lastly, we have 3 protons over here. It's kind of hard to see, but this peak here is a singlet. This one here is a triplet. This one here is also a triplet. And then this one is just a multiplet, so we'll just put an M by that. Also, the chemistry here is a little bit beyond the 3101 chemistry because the reaction between 2-phenylethanol and acetic acid, it's called an esterification reaction. It's a condensation reaction. You lose water, and you would end up producing this molecule. So I'll try and draw it nice and big so it looks good for my annotation. So I have my CH2, another CH2, and then I have my ester functional group over here. So that's the product you would get from the reaction of 2-phenylethanol and acetic acid. And let's see if it's consistent with this NMR spectrum. So the first thing I'll do is I'll label my peaks or my signals. So I'll start upfield and I'll go downfield. So I'll have A, B, C, and D. There we go. So let's see. Well, the only thing that could be a singlet here would be this methyl group. So I would put A over here, and that methyl group, a methyl group generally comes out around 0.9 parts per million, but we're going to add 1 to that because it's alpha to a carbonyl, so that would give us around 1.9 parts per million, and that seems reasonable. We're right at 2, maybe a little bit beyond 2. The next thing I'll take a look at is the big old multiplet down here, the deshielded multiplet, just above 7 parts per million. Those will be our aromatic protons, and there's 5 protons in here. We'll make it really simple to annotate these 5 protons. You know what we can do? We can just circle the whole ring because it's pretty difficult to tell what's going on in this multiplet here. So we can label all of those protons as D, so we can just circle the whole thing. Then we have to look at this CH2 here. There's a CH2 here, and there's a CH2 here. Which one of those should give rise to which signal? Well, if you think about this CH2 group here, I'll just write it in, and I'll erase it quickly. But the one that's next to the oxygen, we would take 1.2 and we would add 3 to that. So 1.2 plus 3. So that means that would give us around, 1.2 plus, so it would give us 4.2 parts per million. So that would kind of line up with this signal here, which is around 4. I don't know, it's hard to see, but it looks like it's in the 4.2, 4.3 neighborhood, something like that. So that makes sense that that methylene would be represented by the letter C. All right, and the last one, B, we'll just stick it in here. And does that make sense? Well, again, if we think about the chemical shift of these protons here, so B, it should be 1.2 plus we should add 1/5 of 3, so that's 1.2 plus 0.6, so that gives us 1.8 parts per million. Is that what we're seeing here for B? It's above 1.8 parts per million, but that makes sense because it's close to the aromatic ring, it's adjacent to the aromatic ring, so it's going to experience some deshielding because of the pi electrons in the aromatic ring. So we could even write greater than 1.8 parts per million, and that makes sense to me. All right, then the last thing to look at would be the splitting. So the only splitting here that we see that's n+1 splitting that we could analyze in our class is the triplet here and the triplet here. And again, if we start with B, this CH2 is coupled by 2 protons, the CH2, so 2 plus 1 gives you 3, so we should have a triplet. And for B, the exact same rationale. It's split by 2 adjacent protons, so 3 and 3. If you need additional help with that, if we were to just write, our CH2 and we have another CH2 and then an R prime, because the two are, so if we said these are the B protons, these are the C protons, again, these two protons are chemically equivalent. They're split by these two protons. So 2 plus 1 equals 3, so that's a triplet. And conversely, if we analyze these two protons, they're going to be split by those two protons. So again, 2 plus 1 equals 3. So we should see 2 triplets. All right, problem solved again.